Hey guys, I'm just going to go over our notes for chapter 12 really quick, and we're going to be talking about gases and the relationship between different variables or different things that can affect how a gas behaves. So this is chapter 12 if you wanted to look through your book. We are not going to be doing calculations of the gas laws, just to simplify things a little bit for you, but I do want you guys to know the relationship between different variables and how they affect each other. Okay, so our learning targets, we're going to describe general properties and behaviors of gases and relate those properties to behavior of the particles that make it up in a gas. So remember our differences between solids, liquids, and gases. Our solids, the particles are closest together and they're moving, but they're just vibrating in place, so they move the least amount. Your liquids are kind of in the middle, and then your gases are furthest apart, and the molecules move the most. Okay? When you increase the temperature of a solid, it's going to melt eventually at its melting point. Because as you increase the temperature, you're adding energy to that substance, which is speeding up the molecules. And as the molecules speed up enough, they're going to then turn into a liquid. And then the same thing happens for a liquid. But instead of changing from a solid to a liquid, it's going to be changing from a liquid to a gas, which would be evaporation. Okay, and again, once those bonds are broken, or attraction between those particles are broken, it would become the gas. So our question now is, what happens when you increase the temperature of a gas? Okay, we're going to look at that and how those different variables affect it. So our kinetic molecular theory is saying that we have a large number of tiny spheres of gas, lots of empty space between it. Those gas molecules are in constant rapid motion. They move in random directions. They bounce off each other. They'll bounce off the walls of a container. No energy is lost during those collisions. We call that elastic. There's no attraction between particles or no repulsion between those particles. The kinetic energy is dependent on temperature. So how much energy is there? Remember, kinetic energy is energy of movement. Depends on the temperature of that gas. And we would calculate that. Again, we're not going to do that, but looking at our kinetic energy has to do with the mass and the speed, the velocity. So pressure is produced from our gas molecules colliding with the walls of a container. So let's think of like a balloon. It's how much force is hitting that per unit area at one time. We use a few different units. We can use newtons or a big N. We can use ATM, which is atmospheres, torr, millimeters of mercury, or kilopascals. And these are our conversion factors between those. Again, I don't think we're going to do any conversions with this unit, but our pressure is going to depend on the volume of our container, the temperature, and how many moles or how many particles are actually in that container. Our temperature measures our average kinetic energy, so how much energy is in the particles. The higher the energy, the higher the temperature. And our SI unit is Celsius, but for gas laws, if I was going to have you do any calculations, they would be in kelvins. So to figure out kelvins, we would use Celsius plus 273.15. That would be our conversion factor. Our other variable is volume, is just how much space is allowed for that gas to be filled. And usually we have that in milliliters. And then moles, which is little n, is going to be the amount of atoms or molecules in a given volume. We can do gas law stoichiometry. Again, I don't think we're going to get to that this year, so you guys lucked out. STP is our standard temperature and pressure. So this would be kind of if a problem said something was at a gas was at STP, that would mean that the standard pressure is at 1 atm and 273 kelvins. Okay, those are our standard temperature and pressure measurements. Alright, so some different laws. We have Boyle's law, which means that when a gas is at a constant temperature, as the pressure increases, the volume is going to decrease. Okay, and we would calculate that P1 V1. So initial pressure times our initial volume equals our second pressure and our second volume. Again, you will not need to calculate these, but they will help you on your simulation lab. So here's a graph, a volume pressure graph, showing that that it's an inverse relationship. So as I keep hitting the wrong button. So as the volume gets larger, the pressure is going to be smaller, which makes sense. Like, think about a balloon. The larger the volume, if the number of particles is the same, there's going to be less pressure than if it's a small. Another example would be if you had like a syringe and you put a cap on the bottom of the syringe. We have the same amount of molecules here. We have a smaller volume on this side. So when that happens, the molecules are going to bounce across and hit the walls more, and that's going to cause a higher pressure, a higher force per area. Charles' law means at constant pressure, as the volume of a gas increases, the temperature will increase. Okay, so it's an inverse relationship. So V1 T1, V2 over T2. Sorry, it actually would be a direct relationship. So here's our graph. It's a direct relationship because as volume gets greater, then the temperature is going to get greater. Or as the temperature increases, the volume increases is usually how we would think of it. So an example could be in the wintertime when you first start your car, your tire gauge, your low tire gauge comes on. And then, inside at that time, the temperature is going to be low, right, inside that tire. But as you're driving it and friction increases the temperature of those gas molecules inside the tire, it's going to fill the tire up again. So the volume is going to increase as the temperature increases. Same thing with the balloon. If you take a balloon outside during the winter or in the cold, it's going to shrivel up. Gay-Lussac's law means at a constant volume. So if our volume is constant, as the pressure of the gas increases, the temperature is going to increase. So this is our gas law, or our equation. It is another direct relationship. So as the pressure increases, temperature increases. One way to look at this is through a pressure cooker. So if we heat up the gas inside this pressure cooker, the pressure is actually going to increase. I was trying to think of another example too, but this is our combined gas law. So again, if we were doing calculations, you could actually relate all three of these together. So it's basically putting all three of those laws together. Our ideal gas law, an ideal gas behaves in a certain way, and so if we have an ideal gas, we could actually use this to figure out how many moles we have. We could actually look at any of these variables. So P is pressure times volume, so our pressure times our volume equals the number of particles we have, or number of moles. This gas constant, which is the same, it's a constant, and then our temperature in kelvins. So again, if we were going to be doing some calculations, then we would look at the ideal gas law, but we're not. So so that's kind of a quick lowdown on our gas laws and how gases behave. Again, what you guys need to think about is the relationships. So if I increase the pressure of a gas, what would happen to the temperature? Or if I increase the pressure of a gas, what would happen to the volume? So those are the types of questions that will be asked. So kind of have an understanding of how those things, how they affect each other. All right. As always, let me know if you have any questions, and I will talk to you soon.